Hello, we are from Group A, Section 2, Group 1. Today, we are presenting a title, Early Detection of Cardiovascular Disease. The reason that we choose detection of cardiovascular disease as our topic is because cardiovascular diseases remain the leading cause of loss of thousands lives globally. Early detection is the most effective intervention to reduce casualty. So this report presents a complete neural network workflow using a feed-forward neural network trained via the backpropagation algorithm to predict the presence of cardiovascular disease based on patient clinical and lifestyle data. This is the case study analysis. Cardiovascular disease detection traditionally relies on standard statistical models or physical charts. However, human physiology is highly complex and risk factors rarely interact linearly. For example, a minor elevation in blood pressure combined with borderline high cholesterol and a sedentary lifestyle might cause compounding risks that a linear model underestimates. So this case study utilizes a data set containing 70,000 patient records with clinical observations such as age, height, weight, gender, systolic and diastolic blood pressure, examination details such as cholesterol level, glucose level, and lifestyle habits such as smoking, alcohol intake, and physical activity. This is a technical implementation of our project. So we leverage Python as the industry standard for deep learning, utilizing its high-level libraries for optimized computational graphs. We use Anaconda as the environment management, TensorFlow or Class for the neural network backend, Pandas or NumPy for data manipulation, Matplotlib and C1 for analytic visualization.
For structural deep learning functions, first of all, we have the activation function, which is a sigmoid function defined as 1 over 1 plus e minus x, and it maps any real value number into a strict range between 0 and 1. This function is placed at the output layer to interpret the final numerical score directly as a probability. Next, we have the dense layer, which is a fully connected layer, a layer where every single neuron receives input from all neurons of the previous layer. The function computes z equals to w times x plus b, where w represents the weight matrix, x represents the input vector, and b represents the bias vector. And last, we have the loss function, which is a binary cross entropy, and it measures the error performance of a classification model whose output is a probability value between 0 and 1, where y represents the actual label and y hat represents the predicted probability. Next, we have input features and variable mapping. The first variable we have is age, which is type integer. And next, we have variable gender, which is type cat, meaning categorical. And we have one for female and two for male. Next, we have height slash weight, which is type integer and float. Next, we have AP underscore HI slash AP underscore LO, which is type integer, and this represents systolic and diastolic blood pressure in mmHg. Next, we have cholesterol slash glucose, which is type cat as well, categorical. And we have one for normal, two for above normal, and three for above normal. Next, we have smoke slash alcohol slash active, which is a binary type, and it is subjective lifestyle features, so 0 for no and 1 for yes. Lastly, we have variable cardio, which is type binary, and the target variable 0 for no disease and 1 for presence.
Now let's look at the actual operational life cycle of our model. This flowchart traces exactly what happens under the hood during a evacuational cycle. We begin by initializing our random weight and bias values. Next, our 11 preprocessed patient features enter the network. This initiates the forward pass. The hidden layer neurons compute their weighted sums and add their pseudo input bias and pass the values through the sigmoid function. Next, we calculate the deviation output error, and at this point, the network encounters a decision branch, which is check the satisfactory performance. If the error rate has dropped within our satisfactory threshold, which is 1%, the loop breaks and the parameter locks, and it ends the loop. If the error is still too high, the network triggers the backpropagation phase, and we vectors the gradient errors backward from right to left, scales them using our 0.2 learning rate, and updates every weight and bias simultaneously. The model then pulls the next batch of data and repeat this exact loop over 60 iterations and until it achieves the optimal predictive accuracy. So for data preprocessing and cleaning, before a neural network can process any medical data, the data must be clean prepared. In our case study, raw clinical records contain massive biological anomalies such as history, blood pressure record at 11,000 and or negative numbers. If we pass these extreme numbers into our continuous sigmoid function, it causes a several mathematical failure known as exploding gradients. The errors become infinitely large and completely destroying the network's ability to learn. To solve this, we filter the blood pressure to variables strictly within very human limits, such as 80 to 220, and diastolic from 40 to 130. For head and weight compared to binary tricks like smoking, head numbers are naturally much larger than zeros and ones. If left unstandardized, the network's summing junction would mistakenly prioritize larger numbers. We applied standard Z-score normalization to ensure every single clinical indicator receive fair gradient attention from the model.
The next one is MLP pipeline. So the first one is forward pass. So the feature feed through hidden layer with sigmoid activation to generate output. The second one is compute error. The machine predict risk compare directly actual patient diagnosed target. The third one is backdrop. Error gradient calculate backwards to update internal parameters. The number 4 is update. So after this project, this flow, the system will update the weight and bias via configure learning rate. Okay, the next one is model matrix evaluation. The evaluation contains the position, recall, F1 score, and support. So we can see that the percentage is 70 something, and the accuracy, the average also 73%. The next one is error rate mitigation map. We can see that the blue one is training cross entropy error. So the error is going lower and lower after the training cycle, same as the orange one. The orange one is validation cross entropy error, but the string is not so stable compared to the training cross entropy error. Okay, that's all.